Okay, Calc. In the last video, we started part A of section 6.5, which is substitution. So finding the antiderivative by substitution. And again, this is for the type of problems where, like the power rule, it's a little bit more advanced than just the power rule. So something that you would have like product, quotient, chain. You have a composite function, so it makes it a little bit harder to do. So you have kind of a messy equation, like one of these guys down here. And you're trying to basically piece them together, and you're going to substitute some things out and end up coming up with an antiderivative that way. Okay, so I'm going to start off. We're gonna do the back side here of the notes, but I'm going to start you off with an example and shows you to show you kind of first of all review over what we did in the last section. And I'll show you kind of what this looks like with the 0 and the 1 in there. So this is a definite integral because it will have those limits of integration. If you want to put this on the back side, you might have some room here at the top to do this. Otherwise, you can grab another sheet of paper or whatever you have handy. But I'm going to show you kind of what this looks like. We need to define a u, and we need to define a du. So we're basically changing our variables again, just like we did before. We need to figure out what u and du are. Okay, so u is always going to be that one that's stuck inside of something else, and that's going to be the x cubed plus 4. Okay, so x cubed plus 4, that's going to be my u. Okay, and then the derivative of u is du, so the derivative of x cubed plus 4 is what I need to do on the right side, which is 3x squared. The 4 is going to drop off, and I did that with respect to x. Okay, and now I start my substitution. Okay, so I'm going to do my substitution from 0 to 1. Okay, so that guy, I just try to cross things off as I rewrite them down below so that I know I've gotten everything. X cubed plus 4, okay, that is now u. So this is now u, and it's u squared. Okay, so u squared is what I'm going to replace him with. And then, really nice, 3x squared dx. 3x squared dx is the same thing as what du is. Okay, so I can just replace him with du. Okay, and then that's what he will look like. All right, so I've got all that figured out. Let me get unfuzzy here. Okay, I have switched my variables, and now I need to take the antiderivative. Okay, so I need to take the antiderivative of this guy right here. Okay, so looking at u squared, I do the 1 over n plus 1, x to the n plus 1 power, or in this case it's u to the n plus 1 power, it doesn't matter what we call him in the middle. But 1 over n plus 1 will be 1 over 2 plus 1, u to the 2 plus 1 power. Okay, and that will actually be 1/3 u to the 3rd power. I think we did that on a problem on the front side here. Yes, it is 1/3 u to the 3rd power because we're taking the antiderivative of u squared. Okay, so, and then I have, usually I would put plus c on the end of here, but I'm not going to do that because we are actually going to plug numbers in. Okay, and so when we plug numbers in, we don't have to put the plus c because the c is going to cancel. Okay, so what I'm going to do is I always put that little line here. And that little line tells me that I've taken the antiderivative, but I haven't yet plugged my numbers in. Now, here is the caution. 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 Okay? You're not going to plug 1 and 0 in for u. We need to switch that back to x first. Okay? So I'm going to switch him back to plugging x in for u. I need to cross him out. U I designated was x cubed plus 4, and now I can go ahead and plug my 0 and 1 in. Okay, so don't try to plug them into 1 or into u because you're going to get an entirely different answer. Okay, so I want to plug them into here. All right, so I'm going to start with the top number. Okay, start with the top number, plugging the top number in. 1 cubed plus 4 to the 3rd power. Okay. Whatever I get for that, okay, I'm going to subtract what I get when I plug the bottom number in. Okay, so I'm going to subtract 1/3 0 to the 3rd power plus 4 to the 3rd power. That's a lot of powers and such. I'm going to end up with a huge number, I fear. okay? And that's what he's going to look like. Okay, so we're still trying to find, this value when you plug those two numbers in, but you need to switch that u out for x cubed plus 4, okay, before you can do any of this. All right, so let's try to simplify some stuff in here. 1 cubed is 1, plus 4, that's going to be 5. Oh my gosh, 5 to the third power is 125. So I have 1/3 times 125, which is just going to be 125 over 3. Okay, minus 0 cubed plus 4, that's going to be just 4. 4 to the third power is 64, I think, and 1/3 times 64 is just going to be 64 over 3, okay? So that kind of comes out nicely because I have a common denominator that I can use. And 125 over 3 minus 64 over 3, if I just subtract those top numbers, that will be like 61 over 3. And I'm just going to go ahead and leave my answer like that. If you want to switch it, 61 over 3 would be like 20 and 1/3, okay? Now think again about like what we're even doing here. What we're doing by getting 20 and 1/3 is we're still trying to find the area underneath of this disgustingly ugly curve, okay? So that's a curve on a graph from 0 to 1. The area underneath of that curve will be 20 and 1/3, okay? So we're still trying to find that area under the curve. Still kind of relates back to that, but since this is such an ugly problem that we can't just do the 1 over n plus 1 x to the n plus 1 for, we have to use substitution to do that, okay? All right, now, there's that process, okay? So we're plugging those numbers in after we find the antiderivative, that type of thing, okay? I'm going to show you an alternative, which some people like better, okay? Same process. Don't think I'm completely switching things. There's one little thing that we switch at the end, okay? So we're going to do this problem. This is second example. We're going to do this problem all the way through, and I'm going to show you one little change at the end that people really like instead. Changing your limits of integration is what it's called, okay? So rather than those numbers being 0 to 1, you're changing those numbers, okay? So what I'm going to do here is they've designated that u has to be x squared plus 1. Okay, that's the stuff that's on the inside. That's what we've determined is our composite function. Du is going to be 2x dx. Okay, yuck. Okay, I'm going to rewrite my integral from 0 to 1. 0 to 1. X squared plus 1 is now u, so this would be u to the third power. So I have u to the third power. And then I need to replace x and dx. Okay, so I have an x and dx here, but I don't have that 2 there. Okay, so what do I do with the 2? I can divide the 2 over to the other side. So divide by 2, divide by 2. Du divided by 2 is the same thing as 1/2 du, and that's x dx. Okay, that's what he will look like. All right. Now, x dx, I'm going to replace with 1/2 du, okay? So this x and this dx, I'm going to replace with 1/2 and du, and that's what he is going to look like, okay? Now I need to find my antiderivative yet, because I've just rewritten him. I haven't even found the antiderivative yet. So that's the next step. I'm going to take this 1/2 and lump him off in front, so we don't have to worry about that. That rule says that we can put that constant number out in front and he can just chill out for a while. So now I just have to worry about the u to the third power. Okay, so I'm going to do 1 over n plus 1 x to the n plus 1 power, or 1 over 3 plus 1 u to the 3 plus 1 power. That 1/2 is just going to chill out in front for a while. Okay, this makes 1/4 u to the 4th power, okay, which all together is going to be 1/2, or 1/2 times 1/4 is 1/8 u to the 4th power, okay? All right, so I found my antiderivative. I don't need the plus c on the end because I'm going to end up plugging numbers in, but here's where this changes, okay? In the last example, what we did was as soon as we got it to this point, okay, I said you had to plug your x back in, and then you could plug in 1 and 0, right? So we had to substitute x's back in for u, and then we could plug in our 1 and 0. What I'm going to do is, rather than changing this back to x and plugging in 1 and 0, I'm going to change my 0 and 1 to be numbers in terms of u, right? So if I plug 0 in for the equation that I have for u, okay, this would be like 0 squared plus 1, okay, and u would be 1 then instead, okay. So plugging these numbers, these limits, into the equation here, rather than plugging the equation back in here, it's just going to save me a little bit of writing. If I do the same thing for 1, so this would be 1 squared plus 1, or 2. Okay, so what's going to happen here is rather than plugging in 1 and 0, or 0 and 1, okay, my bottom number now is going to be 1, and my top number now is going to be 2, because I've switched those. I've changed my limits of integration from x's to u's. So now this u can stay as a u in here, and I don't have to switch him back to this ugly x squared plus 1. I'm doing the same work, but I'm just not like, I'm just saving myself some extra steps rewriting some things. Okay, if I change my numbers in here from 0 to 1 to 1 and 2, then I can just plug them straight into u. Okay, I hope that all makes sense. So 1/8, I'm going to plug in the 2 first. I plug in the top number first. So 2 to the 4th power, that's the first part. And I subtract what I get when I plug in 1/8 times 1 to the 4th power. I subtract what I get when I plug the bottom number in. Okay. So let's figure out what this is. 2 to the 4th power is 2 times 2 times 2 times 2, 16. 16 is what he is. 1/8 of 16 is 2. So I have 2 minus 1 to the 4th power is just 1. So I have 2 minus 1/8, which is like 1 7/8, whatever that is as a decimal. I don't know. 1.875, I think, something like that. 1.875 is my eighths. Okay, so I don't care how you write it as a fraction, as a decimal. You could even put that as 15/8 if you wanted to, whatever. But that's the area under the curve. So I don't care which way you do it. It doesn't matter if you want to change your limits of integration. By doing this process, it just saves you time from having to replace this u back with the ugly x squared plus 1. You've just switched your numbers rather than plugging them, plugging the equation back in and then plugging in 0 and 1. Okay, so I hope that all kind of made sense. Last thing that I'm going to talk to you about is even and odd functions. Okay, so you can't really see this very well, but here is this. Let's say you're going from -a to +a. Okay. And then I'm going to write the integral from here. Let's say you're doing -a to +a of f of x dx, and you're trying to find the area that's underneath of this curve. Okay, if it is an even function, like this parabola is, this is like the equation of some negative x squared function, and you're going from -a to +a. Okay, notice that this half is going to be the same size as this half. Okay, so rather than going from -a to +a, I'm going to make my life easier, and I'm only going to go from 0 to a. I'm only going to find this area here, but then I'm going to double that. Okay, and that makes it so I don't have to deal with the negative numbers plugged in, because plugging 0 in is going to be a lot easier than plugging a negative number in, but I'm just going to double that. Okay, so that's kind of what that rule says, that if you have a true even function, those areas should be exactly the same, and you can just double that area. Okay. Now for an odd function, your notes make this kind of hard to see. If I'm going from -a over here to +a over here, okay, I'm trying to find the area under the curve. So I'm trying to find this area here and this area here. Okay. So if they were to ask me, find the area from -a to a of this function, we'll call him g of x now, so we have a different name than the first one. Then we want me to find the area of this g of x. Okay. If he is an odd function, then that means he is symmetric with respect to the origin. And this area, kind of like an even function, will be the same as this area, except this area is positive and this area is negative, right? Because he's below. But what happens if you have the same area and one's positive and one's negative? Well, they're going to just cancel each other out. So the area of this whole thing would end up being 0. Okay, so that's kind of what they're illustrating up here. If you're going from -a to a, you can just double that and go from 0. I don't know why they wrote 2 up here, but 0 to a. Okay, and this one, if you're going from -a to a of an odd function, then those two pieces should just cancel out and it should be 0. So these are kind of just some shortcuts that you can use if you ever have an even and odd function that you have to do, and that's what they're talking about there, okay? I promise you, if we were doing this in class, I would have you do these over and over and over again, probably on whiteboards or something, but the more problems you do like this and the more repetition you get, the easier substitution becomes, and it's really very pleasant. I really like substitution a whole lot. Okay, so I hope this video helped, and just do a couple of these problems and it will get easier.